In this recording, we're going to learn about exponential growth. So, especially when we're talking about like population growth, which generally grows exponentially, or money, you might have a savings account or money in the bank. It's really important to understand exponential growth. So what is exponential growth? Well, basically occurs when a function increases by a consistent rate over time. Again, not a consistent amount. We're not adding on the same amount every year or every time period. We're multiplying by a particular rate, but that rate is constant. That's exponential growth. So we've got this guy called Bill Unair, great name, right? He happens to have $50,000 in a savings account, and it has a 4% interest, which is compounded annually, meaning he's going to get his interest at the end of 1 year. Okay, that could be worth writing down. Now, 4% is a decent interest for a savings account. You won't find that. More likely to get like a 0.4% interest, right? So it's kind of an unrealistic interest rate, but maybe he has a different type of investment tool, something different than a savings account might get you 4%. But we're just playing with made up money anyway. So let's figure out how much money he'd have after 1 year, where it increases by 4%. So I think you're capable of finding that. Why don't you see if you can find that amount after 1 year? All right, so I'm hoping you paused and worked that out. If not, please do it. You know how to do this. Find the amount. So we're going to go 50,000 times 1 plus 0.04, right? We're increasing by 4%, and that's going to work out to be $52,000. So 4% of $50,000 is $2,000. We're going to add that to the $50,000. That's how much he has after 1 year. Well, the nice thing about compounding interest is the next year he gets 4% not only on that $50,000, but he gets 4% of the $52,000. So assuming he doesn't take any money out, and that's said in the problem. He makes no withdrawals, does not add any more money. So now we're going to find, after 2 years, well, what's 4% of this amount? So figure that out. Play the recording. So we're starting not with the 50,000, we're starting with the 52,000. And you might notice that the amount of increase was not constant, right? In the first year, his bank account went up $2,000. In the second year, his savings account went up $2,080, right? Because he's not simply getting interest on the $50,000, he's getting interest on the $52,000. So go ahead and figure out what it would be for 3 years. Play the recording when you're ready. And so hopefully you took the amount he had after the 2 years, multiplied that by the 1.04. We'll round to the nearest cent. Here we get down to 20 cents here. Okay, so clearly it's not increasing by the same amount every year, but it's increasing by 1%. Well, what if I wanted to jump out and find out for the next 13 years or something? I really don't want to have to find out every single previous year. So let's just kind of look back and see what we did. We took that $50,000, right? And we multiplied it 1 time, 2 times, 3 times. We multiplied the $50,000 by 1.04. So really, I could have jumped out and gotten that amount by doing it all in one step. So let's just kind of think about what that would be. If I have repeated multiplication by, so I got the $50,000, right? Got that. And I'm multiplying it by 1.04 and taking that amount times 1.04, taking that amount times 1.04. How do we represent all that multiplication by the same factor? And hopefully you're realizing, hey, I can represent that a whole lot more efficiently if I do an exponent, 1.04 to the third power, right? Put a comma in there for clarity. So if I wanted to jump to the 13th year, I wouldn't have to keep doing this 10 more times, right? I could just change my exponent to represent the amount of years, and that would be the amount of multiplyings by this base, this rate for the 13 years. Let's generalize. So to generalize into a formula, what that would look like is, if you want to find a particular amount, you're going to start with the principal. We call that P, the amount you started with. And if it's growing, we've got 1 plus R, written as a decimal, raised to the exponent of t. Before we had just said, if we have our initial amount, that's like our A, that's like our P, principal, and I'll probably use this one, use this form, principal amount, that's our 1 plus the R, the rate written as a decimal, and that's our number of years, that's our t, right? So as we generalize this, A is the amount after t years. P stands for the principal, the initial amount. Be careful with our spelling here. So principal is spelled like sort of like principal of your school is spelled this way, not like principles like you have your guiding rules of your life are called the principles of your life, right? Or something important like the principal causes of the Civil War or something, that's spelled PLE, but this is spelled PAL, and that's the initial amount. Okay, R is your annual growth rate. And finally, T stands for time. Remember, that was our exponent in the previous situation. With billionaire, we kept multiplying by that 1.04 every year, so the T stood for the number of years. All right, so okay, as long as we're talking about an annual growth rate, this is going to be measured in years. Okay, so let's try to apply this formula to see what billionaire's account would be in 3 years. We already know the answer. We found it on the previous page, but if we do, we're trying to find the amount, and it's going to be based on the principal. That was our initial amount, so that was 50,000 times 1 plus the rate. Remember, he had a 4% interest rate, so it's going to be 1 plus 0.04, all raised to the t power. So we had 3 times we kept multiplying by 1.04. And if you do that math, 1.04 to the third, and then multiply that by 50,000, you're going to get the same value we got before, the 56,243.20. All right, so I want you on your own to figure out, okay, what did that mean in terms of 25 years? So hopefully if we mastered this process, we could jump out to 25 years. Figure out what that will be and play the recording when you're ready. So hopefully you did this. So with compounding of interest, that $50,000 is going to grow very well, right? It's going to be out to $133,000, $291.82 excuse me. I have one last example I'd like to finish with. Say scientists have stocked this little pond with trout, right? You have 120 trout, and you're expecting it to grow at a rate of 17% per year. Okay, so with that given information and the knowledge you have, I'd like you to find how many trout will be in the pond after 4 years, then try to find out how many trout will be in the pond after 16 years. Play the recording to check your answer if you need help. Okay, so hopefully you did this. You found that in 4 years, so we got our initial amount, 120, our rate, so 1.17 to the 4th power. Now we can't have decimal amount of trout, so it's going to be about 225 trout. Trout's one of those weird words that when we pluralize, we do not actually put a S on the end. It's just trout. Right? For 16 years, starting over that 120 again, that means 16 times we would have multiplied by the 1.17. So I'm going to round that off to approximately 1,480 trout, rounded off to the nearest fish. Thanks for watching.